Okay. I guess I'll start for now. Can you hear me? Okay. Okay. So, today I'll be teaching complete search. So, complete search is like something that's very common in bronze level, especially. Um, so, complete search is like pretty similar to simulation in the sense that there's like no specific like rigid algorithm. Um, the main idea behind complete search is just to try every possibility or like every combo possible. This way we can like try and check all possibilities to try and find the best answer that we can get, which is why it's called complete search. So something very important during contests, you should always try and like come up with a complete search algorithm to like try if you're stuck. So like personally, I recommend that in the beginning you spend around 10 to 15 minutes on each problem, just looking at each problem, trying to find like things that stick out to you, observations that might like transform the problem and make it simpler. But if after 10 to 15 minutes you're still stuck, try focusing on one problem that you think you'll have the highest chance of solving. And then after that, if you're still stuck, then try coming up with a complete search algorithm. Because in some cases, complete search, you can actually take that as like motivation or like a foundation for the full solution. And I have like an example of that later, which I'll show you. So common examples of complete search include checking over all elements. So for example, if you wanted to find the max element in an array, you just check all the elements. That, in a sense, is also complete search. Also checking over all pairs. So like for example, in USOCO problems, it might ask you for like, what's the maximum, say like distance between two cows or something like that. That's also complete search by like checking and iterating over all pairs. Sometimes it could be triplets, sometimes it could be quadruplets, and so on. But you do have to make sure that every time you add like one more to like your pair, you add like an extra O of n factor. So you have to make sure that it like stays within the time limit. Checking over all subsets. So a subset, do you guys know what a subset is? I'm not sure if you guys like learned a subset yet. It's like basically like if you had an array, a subset is just, yeah, just choosing some elements and then leaving the others out. Yeah. And then checking over all permutations is another example of complete search. So I don't actually have like an example where you check for all permutations, but I think it it probably, I think it's shown up in Musica. So I just wanted to give like an example. I just wanted to give like an example of one way you could iterate over all permutations in case in the future you might run into something like this. So we see here, we use C++'s. Oh, you did? Okay, yeah, yeah. So they do exist. Okay. So you can use C++'s built-in function called next permutation. It just takes in a vector and then you stick it in a do-while loop. Now, if you've never seen a do-while loop, do not worry, neither have I. This is the only time I've ever seen it, so. But yeah, basically all it does is like it's a while loop, but it ensures at least one iteration occurs. So yeah. And then the next permutation just generates the permutation in V. So you only have one vector. So it like changes the vector itself. And then you can process it. Yeah. Alright, so an example of a complete search problem. So let's say we had n points, n less than or equal to 100. We want to find the area of the largest rectangle. but the side links have to be parallel to x and y, and the perimeter has to add up to exactly k. So this is like pretty like standard, relatively simple. We see that n is less than or equal to 100, and that's like a telltale sign of like using complete search, because we can just iterate over all 4 points of the rectangle, and that will be like n to the 4, right? Because we have 4 iterations over n, like nested within each other, and 100 to the 4 is just 10 to the 8, which fits within our bounds. So yeah, all we have to do is just iterate through all quadruplets of points, and then you just check if the x coordinates of a pair are equal, and then the x coordinates of the other pair are equal, and same thing with the y coordinates, and then just check that the perimeter is equal to k. And if it is, then you update the answer if the area is greater than the previous answer that we've found so far. So does this make sense? Like what we do for like complete search? Like the idea behind it? Okay. So for some of you who came later, I just basically went over what complete search is. Just a brief summary. It's essentially just trying all possible like combinations that we can, and then just choosing the best answer. So yeah, I have a example problem here. I'll send a link in chat, and then you guys can take a look and try and come up with a solution. A quick note, the problems I have here are actually slightly like on the harder end, so if you can't like come up with anything, that's fine. At this point, just observations are good. Okay, so first of all, does the problem statement make sense? Because the problem statement is like a little bit weird. Okay. So yeah, if you guys like have any ideas, like any like observations are fine too. Even if it seems like really obvious. We should find the number of pairs of cows A and B such that A is between. Yeah, exactly. Okay. So, if I share this tab. So basically, if we look at it, so this is, let's say this is our entry and exit points. There should be 52, but we'll just truncate it for now and only consider A through D, just to make the problem simpler. Right, so we can iterate through all letters between two identical letters for two letters. Yeah, exactly. Yeah, so you guys are right. So like, for example, first of all, the first thing you have to notice is that, like, if you just draw it out, it like makes the problem look a lot simpler, like this. So like, always like just like try and draw things out. But like when you, like for example here, you already see that these lines intersect here because this B is between the A, but the other B is not. You guys see that? So basically, in other words, all we had to do is for every like letter, we find we find the two positions, and then we just check all the letters in between. And if the letter only appears once, then that means we know it's going to intersect. Does that make sense? Because if the other letter was inside, then it would look like this. It would just like be inside of it. But because it's outside, that means the line is going to cross. So this is an intersection. Now, one thing worth noting is that make sure you divide by 2, because if you look at this example, we count the pair A, B, but then when we look at B and B, we're going to find A again. So just make sure that you like don't overcount. And something else, a lot of the times when you see like problems in a circle, you can just try writing it out as a string first. Now this does have some like problems, like for example, if this D wasn't here, but it was like here instead. So on our diagram, it would look like this. Yeah, if it was something like this, then wait, no, not here. Sorry. If this D was like in here, for example, it would look something like this, right? And if we just do it on this string, we won't actually count this pair properly, which is bad. So instead what we do is we actually take this string and we just copy it twice. So that way, like every sub segment will correspond to like n letters on the array. It's just like different rotations of it. Does that make sense? It's like an implementation thing, but it's just like a common trick. So does the solution to this problem make sense? Yes, okay. Okay. So yeah, basically what we just went over, it will cross paths if some letter appears between the same letter only once. So like A something something, B something something, A. And then the B is like outside the A. So yeah. Another problem here. This one's actually a silver problem. Because I think you guys can do it. It's not too bad. So there's the problem I sent in chat. So again, I'll give you guys a couple minutes to think about it. And then I'll explain the solution afterwards. So a hint. If you guys don't have any ideas yet, just So the only difference between the bronze problem, this is a silver problem. So the only difference between this and its bronze version is that the number of cows is less for bronze. So maybe like try and like do a brute force solution. Midpoint of the cows which are furthest apart. Well, the thing is, if it's like weighted a lot, like okay, here I'll draw an example. So this is like something I have. So like if you try and find the midpoint of the cows which are furthest apart. So if I had this one here, or okay, wait, like okay, imagine this one was like really really far away from the rest. Then if you were to find the midpoint, like imagine this was like way above too. Wait, when you say midpoint, do you mean like midpoint as in like the middle cow or the? Because if it's just x coordinate, because then like it will look like this, and then it will look like this, and that's not good. Because we have all the cows. If it's the midpoint cow, it's like the same logic. It could be like heavily weighted towards one section, and that's not. Then it won't be divided evenly. So I'll give you guys a couple more minutes. Okay, so like if like what's like if time didn't matter, how would you guys do it? Like if you had like infinite time allowed, how would you guys? What would you guys do? Like just completely ignoring the time limit. How would you guys do this problem? Check every solution. Yeah, okay. So let's go over the bronze version first. So basically, yeah, so if we just check every solution, for example, we like try drawing the line here, and then we could try like drawing the other line here, and then we just like count each quadrant. And oh wait, I don't wait, okay. Pretend there's one here. Okay. So then yeah, so this would be one way to do it. And then we just like keep trying all possibilities and so on, right? I did not mean to draw like the right solution first try, but that's one way to do it. But the issue is how long will that take? So we need O of n. Wait, we can move in the direction of the larger halves. Yes. But yeah, yeah, okay. Yeah, that's yeah, okay. So basically, if we draw this line, like, okay, so what we do is we can like fix this because we can still iterate over one. So let's say we're iterating this, right? So initially it's like over here, then it's like over here, oh, then it's like over here, and like so on, right? So let's say we got to like this point. Then when we draw this line here, what we can do is we can first find how many points are in this half and how many points are in this half. Because n is only 1000. So we can have an n cubed solution. So by finding all the points in this half and finding all the points in this half while iterating this line here, that's already n squared. So our last dimension here, when we like move this across, we have to do it in O of n. And it's not exactly like moving it towards the larger half, but it's like basically the idea. So what you do is you start here, and then you essentially sweep across. So you assume the line comes over here, and then you have like a index, like an iterator. Not an iterator, you just have like an index for like each of these cows here. And every time our line like crosses it, like for example over here, then we keep like updating like this index. So originally it's here, then it's here, then it's here. Wait, no, sorry, we have two. So the top one is over here, and then after we move it to like say here, then the top one will point over here, the bottom one will point over here. And so as we go, we count in each half, like the top half and the bottom half, how many we've already encountered. And because we've already found all the points in each half, if we know how many we've encountered, that's basically how many are to the left of this line. Sorry, how many are to the left of this line? And then the amount that's to the right of the line is just essentially the total amount in each half minus the amount that we've already covered. Now you might be thinking that like basically sounds like the same thing, isn't it, just as slow? But the thing is, before what we do is like when we draw this line, wait, so we find each line independent. What do you mean? Like, like you don't find each line independently. So like you basically start out finding A first and then B. No. So what you do is you're gonna so this is A, right? Or it might be B, but like let's just say it's A, like this line over here. Then what we do is we initially have A set to like at the very bottom. So it's like basically like the bronze solution, and then we iterate the line upwards, and so on. And at each time, what we do is we count in the top half the number of cows, and then we count in the bottom half the number of cows, like in the entire thing. So pretend there's no vertical line yet, okay? So in order to do that, we're already at n squared complexity, right? So we only have O of n to find the number of cows, to find the best solution if our horizontal line is at this point. So the way we do that is essentially we do another sweep, we call it. And so the line starts here, and every time, yeah, we're fixing A and then iterating all B. Yeah. And then we fix A, and then we move A up again, and then we iterate all B. And so instead of like having this, like instead of, so the reason why our original algorithm is slow is because after this, once we count all these points, and then we move this over here, we essentially forgot we count these points, which is really slow because now we have to count them again. But with this new version, what we do is when we move the line over here, instead, we already know we've counted these points. So we just keep a counter for like how many we've encountered in the top and how many we've encountered in the bottom, which is essentially just like the same as like the index if you sort it in like increasing x, by increasing x coordinates. So that way each cow or each point will only be counted once as we move B to like the right. Does this like kind of make sense? Makes sense. Do other people have any questions? Like this is like a slightly harder problem. It's like harder to understand the solution. So if you have like questions, then you should ask. Okay. Uh, if not, if you guys don't have any questions, then we'll move on with the slides. Okay, yeah. So basically, in the bronze version, in the brute force version, we can just check every A-B combination, but that's too slow for the silver version. So we use this as like motivation. So we fix one of the axes, and then we sort by X, and then we like sweep along, and then we keep track of how many in the top half we visited and how many in the bottom half we've already seen or visited. And as we keep going, we'll increment like the new nodes that we see. And the reason why the time complexity isn't bad is because, like I explained before, in the bronze version, what we do is we essentially count like all the points from the beginning. But in this version, once we've counted a node, we won't keep counting it as we move like our x1 to the right. So yeah. Okay. So next we have recursion. So have you guys like heard of recursion before? Yes? Okay. Recursion is like very important in programming. A lot of algorithms in the future are gonna be like it's gonna be very hard to do it without recursion. It's like, well, yeah, and yeah. So I'll explain what recursion is. So first of all, we have on the left here like a quote unquote normal function. So if you guys don't know what a function is, it's just like basically you can define your own like basically it's like an action, and basically you can call it and it'll do whatever it does that you like defined it. So if I like called func like 10, then it would like have x as 10. And so it'll iterate through all the values and then yeah, print out all the values from 0 to x. So if I call 10, then it'll print out 0 to 10. Now on the right here we have a recursive function. So a recursive function is just a function, except it calls itself, like within itself. So we can see an example here on the right. However, there is an issue. Can you guys like think of any possible issues with this? Yeah, infinite recursion. Yeah, it'll never stop. So, so the reason why it'll never stop is because let's say I call 10, right? Then it's gonna call func of x minus 1. So it's just gonna call itself except with 9. But we already okay, then after that it'll go to 8 and then 7 and so on. But that's like an issue, right? Because it's never gonna stop. It's just gonna like go to like negative like infinity and so on, right? Which we don't want. So what we do is inside we have something called a base case. So if x is less than 0, then we just return, which means it'll like stop the thing from like keep on going. Does this make sense? Like how recursion works? Yeah, okay. Yeah, so basically a summary, recursion just like takes something and then it like breaks it down and gives it back to itself with different parameters. So why use recursion? In general, recursive code is actually cleaner than iterative code. Because of the nature of it, it's just doing the same thing except with like smaller or bigger values. So yeah, in general, the code is like cleaner than if you were to do it like iteratively. It also like helps you break down problems. So for example, if we wanted to do something on the range from 1 to n, and like doing it on like any range is like the same process, except just like a different range, then what recursion allows us to do is like, let's say our original range is 1 to n, then we can break it down into two smaller problems, which is where the ranges are, instead of 1 to n, on the left half we have 1 to n over half, so we cover half the values, and then on the other half n over 2 to n to cover the other half. Then basically we can just keep breaking it down, right? So instead of 1 to n over 2, we had like 1 to m, like m for mu, and then we can continue breaking that range down, and so on. So this is actually like the foundation of a lot of algorithms, and it's why in general in complexity analysis, when you see a log factor, it's base 2, because we're breaking it down into two smaller halves of equal length. And then if we keep breaking it down, eventually it'll just be like 1, like a range of 1. And then when we merge it, the size of each segment will basically we're basically doing the opposite. So after we recurse downwards, then when we want to get the answer, we start merging each segment. So for example, here we would be like merging this range with this range to get this range. And so what that means is that the size of each range is going to double. And if it doubles, then the number of times it can double is limited, right? Because let's say it like doubles x times, then that means we have 2 to the x, right? Because it doubles each time. So 2 to the x is equal to n, which is like our entire range, right? So that means this idea of breaking it down into smaller problems will take log n time, log base 2. Does that make sense? Like where like log base 2 comes from. Yeah? Okay. This is like pretty advanced for bronze. You don't really need to know it, but it's just like, I think it's like pretty cool. And also you'll use it a lot later on. So I just wanted to introduce it now. But yeah, we can like see the power of recursion because it allows us to break like a bigger problem down into smaller problems. Yeah. Okay. So if we had an example here, find the smallest number of coins needed to add up to a certain number of cents. So assume we're using like the American money system. So like a penny, a nickel, a dime, and a quarter. So if we wanted to use the minimum number of coins or the smallest number of coins, our first observation is that each time we use the largest possible coin. So now this idea here of always using the largest or the best possible solution at each step is something called greedy. It's like a greedy algorithm, which I'll be talking about tomorrow more. But yeah, so the first observation we have here is that we always want to just choose the largest coin, right? Because we want to use the minimum number of total coins. So we want to like reduce the amount of change we have as much as possible. So for example, if we used a quarter, so for example, if we had like, we needed to pay off X, then if we used a quarter, then essentially now we only had to pay off X minus 25 cents, right? Does that make sense? Yeah, so this like directly lends us to our like solution. So don't forget the base case. If X is equal to 0, then return 0. Otherwise, if we can use a quarter, then we'll use a quarter. And then notice the plus one. This plus one is because this plus one is basically we're using a quarter, so we're using a coin. Then if it's not greater than 25 but it's greater than 10, then we can use a dime and so on. So yeah, we can see here like how like recursion helps a lot. Right? Because if we were to do this iteratively, how would you guys do it? It'd be like a little weirder. It's like harder to do. This is like much more clean and like intuitive. So yeah, so now we can take this idea of recursion and we can apply it to complete search. So I have a problem here. Which I sent in chat, so. You guys can take a look at it and share any ideas. Oh yeah, also, if you guys could join this other meet, because the meet we're in right now is gonna close soon. So yeah, if you guys could like just join the other one. So, do you guys have any ideas on like how to do this? First of all, does the problem statement make sense? Okay. So, any ideas? Remember, today's lecture is about complete search. Yeah, yeah, just try all 2 to the 10 possibilities. So, yeah, so first of all, yeah, 2 to the m. So basically, first of all, how many total ways are there to choose which air conditioners do we use? 2 to the m, right? Because for each air conditioner, we can like pretend these are air conditioners. For each of them, we have either 2 possibilities. So we can either take this one and put it in our subset, or we can ignore it and just move on, right? So for each one, there's 2 possibilities. So there's 2 to the m, because there's like 2 times 2 times 2 and so on. Yeah, if you guys do like competition math, yeah. So we notice that m is only 10, right? Which means that 2 to the 10 is only 1,000, or like around 1,000. So what we can do is, yeah, 1024. So what we can do is, for each one, we represent it as a string of bits, which sounds kind of fancy. So for example, if we do take it, what we'll do is we'll represent it as a 1. If we don't take it, we'll represent it as a 0. So a full set of all the air conditioners will just be 1, 1, 1, 1, 1. Right? So for now, let's pretend somehow we can generate all of these like possible strings, right? For now. Then how would we do it? You just check for each range. You just like go through, and then for each range, just find decrement like its coldness by like however much it cools it, and then yeah, just check if all the cows are satisfied, and then record the minimum price to do so. So the subset with the minimum price that makes all the cows cool enough. So now the question is, how do we generate this this string, right? Like how are we going to generate all possibilities? Do you guys have any ideas? Binary numbers. Wow. Yeah, okay. So that's one way you could do it. That's actually like decently advanced. So instead of, we can basically represent this binary string as a number represented in binary. So for example, this would be 2 to the 6 minus 1, which is like, what, 63, I think. So yeah, so for example, if this bit was off, then if we take this number like and we converted this to from binary to decimal, this will just be 62. And so this idea of using an integer to represent a string of bits like this is what we call a bit mask, because we're basically like it's like a mask for bits. Yeah, we're using an integer to represent bits, but this is like pretty advanced. I'm pretty sure you only like first see it in gold. So yeah, but the good thing about this way is that we can just iterate from from mask from 0 to 2 to the n minus 1, which is nice because this will cover all possible numbers because of the way numbers work. However, if you do this, you have to like do like bit operations, which I don't think you like. Do you guys know bit operations? A bit? Yeah, they're like. I guess I can talk about them because yeah. So in we have like let's say we have a number 5. There's okay. There's multiple different bit operations. So for example, two angle brackets. This just means that it shifts the mask to the right by 1. So for example, 5 is what 1, right? That's a lie. 101, right? So what right shift does is it basically just like truncates it to this. So basically 5 right shift by 1 is equal to 2. Now we have right shift and we also have left shift. So for example, 5 left shift by 1 is just equal to essentially adding an extra 0 here. So yeah, so what we can do with this is assume we have some random bit mask. So like this, right? This is represented as an integer. I'm bad at math, so I don't know what number this is exactly. But essentially, in order to check if the ith bit is on, what we can do is we can do 1 left shift by 1, 2, 3. And so we basically, if it's on 22, let me check. 8, 4, 22. Wait, that seems kind of. Oh wait, yeah, you're right. Okay. Anyways. So, if we want to check if the ith bit is on, what we can do is we can take 1 and we can shift it I positions over. And so if the operation and of this bit, like of the 1, and the current bit we're working with is 1, then we know it's on, right? Otherwise, then we know it's off. So that's how you would like access like the ith bit of a bit mask, which remember is just an integer. So 22. So yeah, that's one way to do it, but that's kind of complicated. So instead, what we can do is we can use recursion. So initially, we can start out with just an empty string, right? And each time when we recurse, what we do is we can either take like this string and we can add to the end of it either 0 for like off or 1 for on, right? And then we just keep doing this, and we like pass this like to we pass this string back to itself, back to the function. So if we had like some function and it took some string s, then we can add 0 to it, like to the end of it, and then call call func with our new string, right? And then we get rid of the 0 and instead we attach 1 and then we do that, right? And so we just keep doing this until eventually our string is of size m. Then once we do that, then we can call a check function. And then with this binary string s that represents like a bunch of bits, which represents the ACs, like whether we use the AC or not, then we can figure out if like this possibility first of all works, and if it does, if it's better than our previous answer. So yeah, does the solution make sense? If you're confused by the bit mass, I don't think you need to worry about it. Just like worry about this part. Just generating all possible subsets. So does like this part work? Or does this part make sense? Like, does this solution make sense for this problem? Yeah, okay. So, yeah, complete search is like pretty straightforward, kind of like simulation. There's not really much to it. Sometimes when you have like a complete search problem, after you, if you do just like complete search, it might be like too slow. So sometimes you might need like one observation to like speed things up. So like for example, in like the problem where like we like try and like balance all the points, we just like figured out which part of our algorithm was too slow, and we tried to find a workaround to it that made it faster. Usually for bronze though, I'm pretty sure it should be enough to just do complete search. So yeah. Yeah, that's all I have today. Tomorrow I think will be more like lecture heavy because tomorrow I'm talking about greedy, right? So yeah, sorting plus greedy algorithms. So tomorrow there's going to be like more of me lecturing compared to like the past 2 days, which is like just more like problems and things like that. So yeah, do you guys have any overall questions? If not, you guys are free to go. Today's lecture was a bit shorter, but I think it should be fine. Yeah, thank you for listening. Alright, bye.